Hi, this is Shyamala Gauri, Assistant Professor in CSE Department from Rohini College of Engineering and Technology. Subject code CZS 355 Neural Networks and Deep Learning. Unit 1 Introduction. The topic covered in this presentation is different kinds of artificial neural networks. There are several types of neural network models, each designed for specific types of tasks. Below here, I outline some of the basic models of artificial neural networks. First model, perceptron. The perceptron is the simplest form of a neural network and can be considered a building block for more complex networks. Structure. A perceptron consists of a single neuron with inputs, weights, a bias term, and an activation function. Working. The perceptron takes a set of inputs, applies weights to them, sums them up, and then applies an activation function to determine the output. Limitations. A single layer perceptron is only capable of solving linearly separable problems. Applications historically used for binary classification problems. Second model, multi-layer perceptron. A multi-layer perceptron is more advanced version of the perceptron. It consists of one or more hidden layers between the input and output layers, which allows it to handle non-linearly separable problems. Structure. An MLP has at least three layers: input layer, receives input features; hidden layers, perform computations and extract features. There may be multiple hidden layers. Output layer provides the final prediction or classification. Activation functions. Commonly used activation functions in MLPs include sigmoid, tanh, and rectified linear unit. Learning. MLPs are trained using backpropagation, where the error is propagated backward through the network and weights are updated using optimization techniques like gradient descent. Applications: classification, regression. Third model is convolutional neural network. Convolutional neural networks are specialized neural networks primarily used for image processing and computer vision tasks. They leverage convolutional layers to detect spatial hierarchies in data. Structure. Convolutional layers. These layers apply a set of filters to the input data, capturing spatial features like edges, textures, and patterns. Pooling layers. Pooling reduces the spatial dimensions of the output from convolutional layers, which helps reduce computation and overfitting. Fully connected layers. After feature extraction through convolution and pooling, CNNs often use fully connected layers to make predictions or classifications. Applications: image classification, object detection, video analysis, medical image analysis. Recurrent neural network. Recurrent neural networks are designed for sequential data where the current input is dependent on previous inputs. Structure. In an RNN, the output of a neuron is fed back as input to the same neuron in the next time step, creating a feedback loop. This allows RNNs to maintain a memory of previous inputs. Key features: temporal dependency. RNNs are designed to model sequences and time series data where the order of inputs matters. Shared weights across time steps. The same weights are used for each time step, allowing the network to generalize across different sequences of varying lengths. Applications: speech recognition, time series forecasting, machine translation, sentiment analysis. Long short-term memory model. It is a special kind of RNN designed to better handle long-term dependencies and mitigate the vanishing gradient problem that standard RNNs face. Structure. LSTM introduces gates to control the flow of information. Forget gate decides what information should be discarded from the previous time step. Input gate determines what new information should be added to the memory cell. Output gate decides what the output of the current time step should be based on the memory cell and the current input. Key features: cell state. LSTMs have a memory cell that maintains information over time, allowing the network to store long-term dependencies. Gated mechanism. The gates control what information is remembered or forgotten at each time step. Applications: natural language processing and time series forecasting. Next model is generative adversarial network. A GAN is a type of neural network designed for generative tasks where the goal is to generate new data that mimics the distribution of a given training data set. Structure: generator generates fake data that tries to mimic the real data. Discriminator classifies whether the input data is real or fake. Key feature: GANs are trained through a game theoretic approach where the generator and discriminator are in competition. The generator improves by fooling the discriminator, while the discriminator improves by becoming better at detecting fake data. Applications: image generation, image to image translation, data augmentation, deep fake generation. Thank you.